This is what I wanted to show you. Came to springs and what's called simple harmonic motion. If you had a spring attached to a mass, and this would be position A. This will be when the spring is compressed. And then we'll say this is position B, where the spring is in equilibrium, meaning that it's not stretched or compressed. And then it gets all the way stretched out to the place where it's going to be stretched the most. And it just keeps oscillating back and forth like this. That is known as simple harmonic motion. And a couple things you need to know. The stretch of the spring is the same as the amplitude of this oscillation back and forth. If I put this on its side and graph this over time, you'd see like a sine wave. So how far this thing moves from here to here is exactly the same as the stretch in the spring, or I should say compression there, and exactly the same as the stretch on this side. That's also equal to the amplitude if you graphed how that was going back and forth over time. So that's what they're really asking you for. And this is all about conservation of energy. So everything I say about point A is going to be valid for point C. Okay, except here it's compression, there it's extension. But when the block slides all the way to the left, slows down, stops just that 1 second before it turns around, speeds up the other way, that is for both A and C. That is where your velocity goes to 0. So that's where velocity equals 0. Therefore, your kinetic energy is 0. So it's at its minimum. However, this is where you have the most stored energy in the spring. That's where that is at its maximum, because it's compressed the most. So it's just 1/2 kx squared. The higher the k, I'm sorry, it's going to be the same spring, so it's got a set k. The higher the compression or extension, the more force is in it and the more energy is in it. This will be where the force in it, which is kx, is also at its maximum. So if F equals ma, that also means your acceleration is at its maximum at these 2 points. All right, that's where the force is biggest on this mass. That's where the acceleration is going to be the greatest. Now at point B. Point B, you get the entire transformation of this 1/2 kx squared in the spring becomes now the moving motion, the kinetic energy of the block. So here, your V is at its max. Therefore, your kinetic energy is at its max, where you're moving the fastest and have the most kinetic energy. Since the spring is not compressed, that means the potential energy in the spring is 0, or at its minimum value. That means that the force in the spring is at its minimum because it's not compressed at all. And that's where your acceleration for that moment in time is at its minimum. So this is all about transformations of energy. It's going from potential energy in a spring to kinetic energy, total transformation upon reaching the equilibrium position. And then it goes to stretching it out, potential energy in spring, back to kinetic energy of block, to potential energy of spring, back and forth, back and forth. You could do this also for pendulums. The formula for the period of a pendulum is something that I have a standalone formula. I have you guys just go look it up and learn it on your own. Same thing for a mass on a spring. There's another formula for that period. Look it up. This is going to be, instead of becoming potential energy in a spring to kinetic energy moving to potential energy in a spring, it's gravitational potential energy, because there's no spring here, to kinetic energy to potential energy. So when you're here and you're at your H max, that's where your potential energy is at its maximum. Your V here just goes to 0 for that moment in time. You get a total conversion of potential energy to kinetic down here. This is where your kinetic energy is at its max. This is where you're moving the fastest. Similar to what's going on up there. So you can set, we'll say this is A, B, C. You can set kinetic energy at B equal to the potential energy at C if they're asking you to solve for the velocity down here. There's also one more thing I want to show you on this. There's going to be a problem on the test where you have to figure out what this potential energy is, so you need that height off the ground. Well, you're going to be given like the height of the string, I don't know, 2 meters, whatever you're given. And you're going to be given this angle. So this is the same string, so it's going to be 2 meters here. If you make this triangle, you could find this side using cosine. If you subtract that from the overall length of 2, you'll find the height off the ground. That's what you'd plug in for the MGH, the H over here. And one last thing, there is a problem also about a ride at a, I was in view when I did that. Amusement park ride, which is a swing turning around. There's going to be like a post in the middle which spins. There's going to be like a wooden platform or whatever on top like that. And this swing is going to be off at an angle, swinging like that. It's going to be moving in circular motion. This is the radius of that circle. So to figure that one out, you're going to have to similarly drop a perpendicular down to here. You'll be given that angle. Use sine to figure out that distance. Then you got to take the radius of whatever this is, add it to that, and those two numbers added together is actually the radius of your circular path. So when you do sum of the forces centripetal equals mb squared over r, that is this whole distance. That's what I wanted to tell you.